Hey everyone. Well, today's a bit of a technical video. There's been a lot of people doing 2GR swaps lately, and one of the things that's come along with that is people wanting more than that 304 wheel horsepower that I've been able to get with the combination of parts that I have. And one of the things they've been reaching out to is the Monkeywrench racing cams, particularly these stage 2 cams. And there's a couple people out there that have gotten really nice results. Unfortunately, there's been a lot more people that have gotten some rather disappointing results, and some people that get motors that don't even run. So today I really want to explore perhaps why that is. I don't think we're going to get quite to the bottom of it, but I think we're going to get some more ideas of where the problems might be. So stick around and let's get into it. So an opportunity presented itself. Ty over at TCS Motorsports had a 2GR-FE with stage 2 cams installed, and he was willing to let me crawl all over the engine and measure the heck out of whatever I wanted on the engine. So that was fantastic. That means I didn't have to spend $1,000 buying cams just to measure them. The reason I wanted to do this is because I've been getting reports back from 310 wheel horsepower all the way to 350 wheel horsepower. So obviously that's a pretty big margin, especially when you consider, you can see this run here actually at TCS Motorsports on Ty's dyno again, getting 304 wheel horsepower. And yeah, so that's gains from 2% to 15%. That's a huge margin. And I don't think a lot of people would be doing this, these cams, if they knew that it was only going to get them an extra 6 wheel horsepower. Obviously, it's not worth it. So there's a cause for concern there, and an even bigger cause for concern is lately some people are reporting some misfire codes which are making the stock ECU unhappy. For some people it's just a couple misfire codes that show up and nothing bad happens with it. They're just there, and that's annoying in itself, but at least the motor's still running properly. And in some cases the misfire codes are making the motor go into limp mode. I think the limp mode in this case is because it's trying to protect the catalytic converters from overheating and catching on fire. So it's a pretty decent reason. This ECU really doesn't go into limp mode for very many reasons, but not catching on fire seems like a pretty decent reason. So what you can see here is I did just that. I spent several hours going over the motor. In particular, I was measuring the cams, the center line and the lift and the duration and all that stuff. So there were a few things that stood out here. The first one is the lift. The Monkeywrench racing cams here have a base circle of 36.2 millimeters, which is reduced from 38 millimeter stock, with a 6.7 millimeter of lift at the cam. That means about 11.5 millimeters of lift at the valve, assuming zero lash. This isn't too far from the advertised 11.67 millimeters of lift, but it doesn't feel like a great number. And I also wanted to measure the duration of the camshafts, but the hydraulic lash adjusters were making it difficult to get an exact measurement. It felt a bit shorter than the stated 266 degree. I can't confirm because of the hydraulic lash adjusters making measurement a little bit harder. And something to note is the stage 1 cams are about 11.5 millimeters of lift and 10 degrees less duration. So I'm going to go on the assumption here that maybe there was a shipping mistake and these stage 2 cams are actually stage 1 cams. So I'm going to ignore the lift discrepancy and the duration discrepancy, and we're going to explore center lines from now on. But the really nice thing here is we can use the power of the crowd. I'm sure there's a couple of you guys out there watching right now that actually have Monkeywrench racing cams. So if you guys could measure the base circle as well as the total height of the lobes, that would be great. And yeah, and report also which stage you think you bought so that we can get some numbers. I really hope that what the issue is here is Monkeywrench just shipped the wrong cams. There was no markings on the cams, so we couldn't tell if that was the case. So yeah, leave it in the comments if you can. Base circle and lobe height and which stage you think you bought, and I would really appreciate it. And if you want to stay anonymous for some reason, feel free to send that to me over email. If there's interesting data that comes from that, there will be a follow-up video. As mentioned earlier, the hydraulic lash adjusters made it so that measuring the exact duration and lift was going to be tricky. What was going on is these Monkeywrench racing springs are really stiff, and we'll get into that discussion in a little bit here. But essentially they were collapsing the hydraulic lifter. When I was setting up the 2AR, which has pretty much identical valve geometry, that didn't have that issue. The hydraulic adjusters, the hydraulic lash adjusters stayed fully pumped up while I was measuring, and that was wonderful. But in this case, what I had to do for the test procedure is I just put the valve at maximum opening. I went ahead and let the whole thing collapse all the way, waited for the movement to stop, and then I was able to back up the motor, move it forward to take up all the slack in the chain, measure my height, measure my angle, go past the lobe, go back to the same exact height, and then you measure your angle again and you can get your center line. The measurements were repeated at least 3 times, and some were done 4 or 5 times with different setup operations to confirm the data that I found, especially when the data was suspicious. The measurements were usually within a half degree of repeatability, though I certainly made many mistakes reading the degree wheel because the angle is awkward and whatnot. So there was a few numbers that were just way out there, but those were easy to throw out because once you got the right number, you're able to repeat it within a half degree. And the results are right here. So I spent all that time measuring, and yeah, I see a whole pile of numbers here. And what it came down to is all of these center line numbers here, and I went ahead and from these center lines I subtracted 180 degrees from every subsequent cylinder. So cylinder 1 I subtracted 0 from, cylinder 2 I subtracted 120 degrees from, cylinder 3 was 240, because this motor fires every 120 degrees and the firing order is 1, 2, 3, 4, 5, 6. So what that gave me is some center line numbers here that were all lined up as if they were firing at the same time, and that allows me to compare them really easily. Then I was able to use, oh, let's see if I have it here. Yeah, then I was able to use this guy right here. That's right out of the factory documentation. That tells me what the center line is supposed to be on the cams, and I was able to subtract that from here. So then the results that I got, the bank 1, so that's the rear bank on the motor, the intake cam was pretty much spot on. So center line was ground exactly where it should have been. The exhaust was 1 degree advanced. Not a huge cause for concern. You know, it's hard to set them up exactly in there. Now, bank 2 is where things get suspicious. So if we go with the exhaust there, the exhaust is 3 degrees retarded on the center line, and the intake is 5 degrees on average retarded on the center line. Now, I say on average because cylinder 2 was more retarded than cylinder 6, and by more than my test accuracy that I would have expected, so by 1.5 degrees over the whole thing. So that's a little weird, but even if we ignore that, the fact that it's 5 degrees off that seems suspicious, seems sloppy. And conveniently, by the error being on bank 2, we can eliminate the possibility of chain stretch. First of all, this motor is a 4,000 mile motor, so chain stretch is unlikely, but the motor pulls, it goes from the crank to bank 2 and then to bank 1. So any stretch that we would see on bank 2 would be seen on bank 1 also. And if it is chain stretch that's showing it on bank 2, then that's fine. It just means that instead it's bank 1 that's ground off center line instead of bank 2. So the results are still valid. There's a very, very small chance that the results are actually inverted from what I think that they are. So let's see if we can quantify what this data means. I used a desktop engine simulator, and these are far from perfect. I totally understand that, because it's often a case of garbage in, garbage out. I put as good a data as I can in it, and we can see the result. But what we can use it for is for the trends, right? Because whatever the engine that I put in is, that is going to be the exact same engine minus 5 degrees on the cam, so we can compare and get some relative numbers. But conveniently, what I did is I entered a motor, a 3-cylinder motor that was exactly half of it, because we want to see what happens if one bank is off and not the other. So we got a half a 2GR in here, and conveniently it fell right on the perfect numbers. What you can see here is about 200 at the crank, so 400 at the crank, take 15% drivetrain losses out, and you're right at that magic 350 horsepower that we actually have seen some people get on the dyno with these cams. So really happy it landed on that. That's great. Now let's go ahead and throw the cams off by 5 degrees. As you can see, it loses about 8 horsepower, maybe 10 or so. So if both banks were off in the opposite direction or something, you could be looking at 20 horsepower. Technically, that could be adjusted in the tune if both banks were off in the same direction, but only if you notify me when you order the ECU or if you're using an aftermarket ECU. But often, actually I haven't seen a single aftermarket ECU that lets you set different targets for the front as well as the rear bank. So if they're off by different amounts, you just can't make it up in software. Now, I'm sure that's an incorrect statement. I'm sure there actually is an aftermarket ECU and probably the Motec that can target different VVTI angles, but even that is inconsequential because the way that the VVTI system works, it really doesn't like sitting between 0 and 5 degrees. So if you have one that's 5 degrees off from the other, you're eliminating your ability to use between 0 and 10 degrees on the whole system. So that's still not great, even if you can fix it with the ECU. So then let's see what happens if we put stage 1 cams in instead. Magically, the engine simulator right there, look, it went right down to 310 horsepower. That was with me keeping the 5-degree offset on one of the intake cams, and that's our magic number, right? That's what some people are getting. Now, does that mean that many incorrect, stage 1 cams are being shipped instead of stage 2? Maybe. So what I went and did instead is what if I leave the stage 2 cam specs instead, and instead I set about a 0.5 millimeter of valve lash, and take a look at this. Well, 315 horsepower to the ground. So let's talk about the lash. Let's talk about why I put in a 0.5 millimeter there. I really do feel that those 230 pound per inch springs that Monkeywrench Racing sells are way too stiff for this engine. One thing I noticed while I was doing this is some of the lash adjusters are collapsing really quickly and some of them are not. Now, in theory, the design, and you can see the design right here, that's a check valve. Now that's metal on metal, so it's potentially not going to be a perfect seal, but on all the previous motors that I timed before, which have all been ARs, but again, it's the exact same lash adjuster, they haven't collapsed, and those were with much lighter springs, stuff in the 130, 150 kind of range. So yeah, there's oil pressure missing, and the oil pressure will certainly try to make up for that, but I think that some people are going to be experiencing hydraulic lash adjuster collapsing, and that's why they're getting these issues. And they might also be explaining some of the issues with the balance and the misfires. Let's say you've got a hydraulic lash adjuster that's collapsing more than the others, even though it's still perfectly fine according to Toyota spec with the lighter springs. At idle, when your valve spring has even more time to collapse, that could be unbalancing the cylinder enough. Keep in mind, the motor only has, the motor's computer only has feedback on each bank. It can't tell individually if cylinder 1 is running richer than cylinder 3 or 5. So by having an imbalance there, your air-fuel ratio could get really bad, even though the average of it would be perfectly fine. And maybe that's what's causing our misfires. And keep in mind, with the 2AR, again, with an almost identical valve train, I had a much lighter valve spring, and I was able to go to 8,500 RPM. Now, I want to say safely and in a durable way, but the truth is I haven't actually put a ton of miles on it. So we need to take that with a grain of salt. Maybe the spring that I used is not adequate, but I like data. I like data. So how do we get real data on that? How do we avoid putting these 230 pound springs in there and also avoid spitting out rockers at high RPM? Because obviously 8,000 RPM that we're trying to achieve here on the 2GR is way more than the 64 or 6,500 that these motors are rated from the factory. And the obvious answer, of course, right here is a Spintron. And that right there is a stupid expensive machine. But instead, if we kind of just push that out of the way and we try to imagine what a Spintron does, we end up at a under $200 solution. And conveniently, because this is an overhead cam motor, we don't have to spin the whole motor in order to figure out what the valves are doing, because our cams are in the head instead of in the block. And this is a stroboscope, and the reason I've got the video right here is I just want to show you guys quickly how it works. So let's turn the lights off. I'm going to spin this up. Actually, I'm going to go ahead and spin this up with the lights on so you can see what this thing is doing, and then I'm going to turn the lights off and I'll turn the stroboscope on, and we'll be able to see what that does and how that could possibly help us. Now, there is going to be a bit of flashing. I'm going to do what I can to set the exposure in a way that it minimizes the flashing. But if you are sensitive to flashing, please just skip to this part here in the video, and that's where I will resume this discussion after I show this little demo. So we can stop the motion, we can rotate it to wherever we want. So this will allow us to explore exactly what's going on with the valves once we spin it up. You know, we can go right to the critical points, and we can see if the rocker is losing contact with the valve. And of course, we can push it beyond its rated horsepower, beyond its rated RPM, and see where it starts to have problems. So anyways, really useful tool. So yeah, so as you can see, this $200 tool right here will be fantastic. It's going to substitute what would have been a tens of thousands of dollar camera that, sure, I would absolutely love to have a slow motion camera, but we don't have the budget for that. But instead we'll use that, and I'll just use the VFD that you see up there to be able to just use a 3-phase motor and vary the RPM that the valve train is seeing. We should be able to simulate somewhere in the 10 to even 12,000 RPM range, and really be able to push to find where the limits of the springs are. And of course, since it's not sitting in the motor, it'll be easy to just add a little bit of weight to the valves if we want to see kind of the effects of that, to simulate different valves that are potentially on the market, and determine with this cam and these valves and these springs, we start getting lift off at, 11,000 RPM. These are answers that we'll be able to get exactly, and that'll be wonderful. That'll reduce the amount of friction that we see in the motor. Hopefully that'll reduce the amount of lash adjuster collapse that we see in the motor. And actually, that's another thing too, right? We'll be able to see just how much the lash adjuster is collapsing using this. So hopefully we won't see any of that, but maybe we will. And certainly, if we see too much lash adjuster collapsing, then the answer becomes easy, right? We need to release a product to make solid lash adjusters. Solid lash adjusters are a bit of a maintenance nightmare because you have to disassemble the motor in order to shim it, and in this case with this motor, the disassembly required to get to those is really kind of a pain. So I want to avoid solid lash adjusters, but if we have to, we'll know if we have to, and we'll know the kind of conditions that'll require them, so hopefully most people won't need them. So back to the original problem that brought out this video. I really think that the people that are getting 310 wheel horsepower from the Monkeywrench Racing Stage 2 cams probably actually have Stage 1 cams installed. Thankfully, that's really easy to test. You can remove the valve cover and measure the lift and the base circle of the lobe, and you can confirm that. Because really, from the inaccuracies on the centerline that I'm seeing, I really can't, even if I imbalance the air to fuel ratio along with the centerline difference and kind of get the motor in the worst possible condition that I can get it in, where the stock ECU would do, where you don't have the aftermarket ECU to be able to correct it, I really can't get the cams to lose much more than about 20 horsepower. Now, 20 horsepower is still very significant, and I think that should be a cause for concern. I'm not really liking the inaccuracies on the centerline that we found, but I don't think that's the whole thing. And unfortunately, normally when you get regrinds, you put adjustable cam phasers on there so that you can phase your cams exactly, you degree them in and your motor run properly. But in this case, we've got 4 cams that all have VVTi on it. There's no way to adjust it. So they have to be ground properly, and if they can't be ground properly, they have to be binned so that your intake cams are the same and your exhaust cams are the same. And then it's easy, right? You can tell me when you're ordering a tune, hey, I've got stage 2 cams and they're 3 degrees advanced, or I've got stage 3 cams and they're 5 degrees retarded or whatnot. And then I can easily make that adjustment in the tune. Obviously, it might affect idle quality, because at idle where the cams are locked, that will change things, but 5 degrees one way or another won't significantly affect your idle quality. I really do think the idle quality has more to do with the lash adjusters collapsing from the springs that are too heavy. So overall, I don't think that any of this data was 100% conclusive. I think it hints at some issues, but I was really hoping for a big kind of gotcha. You know, what I was hoping that we'd find is a couple of these lobes that were ground on very different center lines. Like even the 1.5 degrees that I found, I don't think that's enough. But on a regrind, you can only be so far off before there's no meat there to regrind anyway. So that 5 degrees is probably towards the maximum error that these things can have. So I guess that means we really do need to make that Spintron, and we need to figure out what spring rates we can use and see if we are having lash adjuster collapsing, and figure out how to deal with that. So on that note, I guess that's a teaser for a future video, and we'll see you guys later. Bye.